Hello, I'm Emre Erçelik. Welcome to the numerical examples of stress-strain projection theory. I recommend you to watch the 4-video playlist first, then practice on this video. In this video, we will solve 6 examples and take a look at their programming aspects. The first example is the simplest case. Consider the one-dimensional rod. We will project the stress values onto nodes. This is the solution of example 1. As you can see, stress-strain field is just shape functions defined at Gauss points. If we multiply respective values with Gauss point shape functions, in this case 3 and 3.8, we get the stress field. The shape functions are already available to us. The shape functions are defined at the nodes. The mass matrix is 2 by 2 because there are only 2 nodes, and the projection result is given below. And you may try to extrapolate the field function to -1 and 1. In its simplest form, L2 projection is equal to direct extrapolation of the field function. The second example. 2 rods assembled from their tips. We will project the stress values on the nodes. We applied the same procedure with the first example. However, in this case we have 2 mass matrices and 2 force load vectors. The global system is 3 by 3. We have G1 and G2 in the force load vectors. They correspond to field functions of the elements. And you may try to extrapolate field function to the nodes. The extrapolation result is given below. The projection and extrapolation plus averaging gave us quite similar results. But how do we test which one is more accurate? We can guess back the Gauss point values based on nodal values of extrapolation and projection. You can try it. The mean squared error of the projection is lower than extrapolation. This means projection is better at minimizing the difference between F and G. In addition to this, L2 projection created 3 values which are continuous. Extrapolation can be continuous only between 2 adjacent elements, not for all structure. We have some observations. The first example was already on natural space. Therefore, we did not change anything, directly calculated. The second example was not on natural space. However, we implicitly converted the elements to be on natural space and we performed calculations. This is the correct way of projection technique. We do not need physical space coordinates. The technique is on natural space and independent for every element. Thus, next examples do not contain coordinate data. They only contain stresses. The natural space coordinates are already available to us. We will just use them. The third example is one linear quadrilateral element. We will project the stress values onto nodes. And this is the solution. Again, stress field is just the shape functions defined at Gauss points and multiplied with stress values. This field function creates a surface in 3-dimensional space, like in the third video of the playlist. This field function is the reason why it is called linear quadrilateral element. There is no quadratic component like xc squared. The mass matrix creation is the same as former examples, but more complex. The projection results are given below. Now again, you may try to extrapolate field function to the nodes. In its simplest form, L2 projection is equal to direct extrapolation of the field function. Note that the average of the nodal values add up to 5.925, which is exactly the same as the average of the values on Gauss points. The fourth example, 2 linear quadrilateral elements. We will again project the stress values onto nodes. For simplicity, the left side element is the same as former question. The first step is to solve for the left side element, but we already calculated its respective values. Therefore, we can just insert them in corresponding locations. We will calculate the right side element, then sum the mass matrices and force load vectors. Finally, we will solve for the global system. The solution for the right side element is given. Now we just have to sum the mass matrices and force load vectors, then solve for the global system. This can be done with a short script. The result of the system is the projection result. You can compare the results of extrapolation and projection. At node 3 and 2, they guess quite similar results. Again, we have some observations. We cannot calculate a unique mass matrix for every element and sum them to get a global matrix. Because we had only 2 elements, the inefficient algorithm was our approach. If we want to scale up this projection, we have to construct 2 for loops going over initiated global matrix and 1 for loop for force load vector. The index loop directs the for loop between nodes and shape functions. The index loop for the right side element is given. And the fifth example, 3 linear quadrilateral elements. We will project the stress values onto nodes. Again, for simplicity, the downside elements are the same as former question. A question arises. Do we really need to calculate for every element? No. We already know the contributions will be made by the downside elements from former question. In addition to this, we have some shortcuts. Shortcut 1. If you are careful enough, you would notice that the mass matrix integrals are always repeating values, because we are always integrating same functions. The integral is either 0.444, 0.222, or 0.111. However, this is not for your computer. It's just a fast way to proceed on your paper calculations. And the shortcut 2 is we can construct index loops for elements to proceed fast. And index loops are given below. But how do we use index loops? You can try to guess mass matrix contribution will be made by the upper left element at index 8, 7. The corresponding shape functions are n4 and n3. Therefore, it's 0.222 by shortcut. With this approach, lots of heavy work becomes a loop. It becomes an automatic calculation. The only thing we have to do is to create a short script that selects shape functions and indices for us. Here you can see a simple version of L2 projector. Field functions are calculated, element index loops are created, element list is created, mass matrix and force vector are initiated, then the loop runs. If you successfully calculate the mass matrix and the force vector, these are the results. The extrapolation of the node 3 is 1.821 and it's nearly the same as the projection result. And this picture shows the corresponding calculated node values. For the last and the hardest example, consider the 4 linear quadrilateral elements. Again, we will project the stresses. For simplicity, left L shape is the same as former question. The same approach, without changing anything other than adding an element, the same algorithm also works on 4-element structure. If you calculate the mass matrix and force vector on paper, these would be the result. Again, node 3 extrapolation and projection results are nearly the same. And this picture shows the projection values as well as the Gauss point values for the last question. Again, we have some observations. Field functions are just shape functions defined at Gauss points instead of nodes. We go over every node of every element multiple times. This can be easily done on a computer with a loop. We stored element data in a list. We called it index loop. Also, we stored field functions in a separate list. Lists are primitive structures. We can create a D2Q4N object to store data in an advanced way. Extrapolation is inserting natural space coordinates of nodes in field functions. It's a way of approximating. Again, we are not in physical space. Extrapolation and averaging gives nearly exact results with L2 projection. However, it's not continuous for all structure. Both ways can be used to smoothen the plots. However, L2 projection is just better. I hope you solved the questions and understood the algorithm of the approach. And thank you for watching.